Well, thank you all so much for coming. We are a senior design group from Gonzaga University. Our project is called the Stormwater Treatment Monitoring Project, and we are a multi-year project partnership between Gonzaga University and Spokane County. My name is Bella Burzynski. My colleagues are Nicole, Chen, and Leland O'Hanlon. Our project advisor is Dr. Aimee Navickis-Brasch, and our project sponsor liaison is Ethan Mernon, who is a representative from Spokane County. So Brandy touched on some of the intro stuff for bioretention, but just to go over it again, a bioretention cell is just a vegetated depression with a combination of engineered soils and vegetation to reduce stormwater pollutants. Here we have a picture of our project site located on Gonzaga University's campus. We have a dual cell bioretention unit, so there's two different cells within the unit itself. The main difference between the two cells is the bioretention soil media, or BSM depth. One of them has the Ecology required 18-inch BSM depth. That one's the one on the right, and then the other one has a 12-inch BSM depth. Other than that, the two cells are the same. They're both have grass as their vegetation, and then beneath the BSM there's 12 inches of sand, followed by 6 inches of wash drain rock surrounding the underdrain, which the stormwater runoff conveys to. Here we have an image of the contributing drainage area of the site. Let's see if I can, this little tiny dot right there, that's our site. All of the green area is impervious area, including a parking lot and then also that walkway right there. So all of the water drains to our site from that area. Brandy also touched on this a little bit, just to go over ecology requirements for the bioretention cells. These are approved in Western Washington. However, we're applying them in Eastern Washington and Spokane. An 18-inch BSM depth with 60% compost, or sorry, 60% sand, 40% compost is approved to reduce pollutant concentrations of TSS, dissolved copper, and dissolved zinc as well. So we have two main goals for this study. The first one is to advance an understanding in the treatment performance of the 12-inch versus the 18-inch BSM depth. This could potentially save on construction costs if the 12-inch BSM performs as well as the required 18-inch BSM depth. Our second goal is to advance an understanding in the treatment performance of the cells during cold climate conditions, specifically when deicer is used on the contributing drainage area of the project site. So to complete these two goals, we had several objectives that we met throughout the study. The first was to conduct a literature search just to familiarize ourselves a little more with bioretention and the pollutants of concern for this project. Then we collected stormwater samples from the site using an automated sampler, and we sent them to a lab to have them analyzed for our pollutants of concern, which include TSS, total phosphorus, or TP, dissolved copper, and dissolved zinc. And then finally, we analyzed the pollutant reduction concentrations by creating a statistical analysis. So the first objective that we had was to conduct a literature search, and these are just some quick points from some of the pollutants of concern, some things that we found. With TSS, we found that there was not really an impact on the pollutant removal in cold climate conditions unless frozen soils were present. This is mainly because TSS is removed with mechanical filtration, which is not dependent on temperature at all. And then as far as the influent concentration of TSS, we found that, or the literature search that we conducted showed that there was a higher concentration of TSS in the influent due to use of aggregate on the roadway when it's icy out. And then for TP and dissolved copper and dissolved zinc, there were a lot of varying results. I know Brandy touched on that. This could likely be due to the varying BSM compositions that we found across the studies. We're not really 100% sure about that. And then after we conducted our study, or we collected samples and analyzed the data, we continued our literature search a little bit more just to continue learning about what we found. So we did a little bit more research on cation exchange capacity and sodium absorption ratio within the BSM, just how those are effective. We'll be talking about that a little bit more later in the presentation. And then we also found a little bit about hardness. So we found that hardness decreases the toxicity of metals based on the biotic ligand model. However, hardness is not a parameter that's required to be tested by Ecology. We just found trends in our data that suggested an increase in hardness, and so we wanted to dive into that a little deeper. That'll also be mentioned later in the presentation. So that was our first objective. As far as our next objective, I'm going to hand it off to Leland, and he will be talking about the data.
So we attempted to collect on 5 storm events in our storm collection period of October to March. Of those 5, we only actually collect on 3. And of those 3, one of those didn't meet qualifying conditions due to it being less than the required 0.15 inches of rain. The 2 that we weren't able to collect on, it was because of the temperature was too cold out, and so the samplers wouldn't collect. Here you can see our storm data. The first storm we had was on 11/22. This had a depth of 0.08 inches, which did not meet the qualifying conditions. Our second event was on 12/17. This had a depth of 0.41 inches of rain and a storm duration of 20.5. And then our third event, which was on 1/17, had a storm depth of 0.26 inches of rain and a storm duration of 11.3 hours. This is our pollutant removal data. It has our data that we collected this year, which is events 4, 5, and 6, and also the data that was collected last year, events 1, 2, and 3. This was done so we have more data points when we look at analysis. For TSS, our last 2 data points, 5 and 6, we decided to ignore because the influent concentration coming in was too low, and so they weren't like very good data points, so we decided to ignore those. And those averages then become around 80%. This table also includes our statistical analysis that we did. So we did the influent versus the effluent for both the 12 and 18, along with doing the 12 and 18 versus each other. From this, we saw that there was a statistical difference between the inflow and outflow, which means that there was change within the BSM. And then we also did the 12 versus 18, and we saw that there wasn't a statistical difference between them, which resulted in that they're roughly working the same for all 4 pollutants. These are our concentration effluents versus our concentration influence. This shows the removal kind of within it. On the left is TSS, and on the right is total phosphorus. As you can see, total TSS had a very declining, and then the last 2 data points are the ones that we're ignoring again. But we did have a jump in that first one. And then with total phosphorus, we see that it's all above 1, which indicates that we are leaching total phosphorus. But within the 2 years, you can see that the trend is declining. These 2 graphs are for dissolved copper and dissolved zinc. As you can see, other than the one point that seems really high, our dissolved copper seems to be relatively stable and decreasing. That means we're keeping relatively the same dissolved copper removal. And then with dissolved zinc, you can see last year's trend was going up, which means our removal efficiency is going down. While this year we have a trend that's going down, which means we're increasing our removal efficiency. And so then we took some hardness data points, and we saw that we have a really high hardness leaching occurring. So this made us want to go look back at last year's data and see what they had. And from that, we determined that we have a high leaching, increasing trend going on. This made us want to look more into hardness. And this is where Nicole is going to come and talk more about what we did.
So since we saw an increase in hardness concentration at our project site, we decided to perform a column test. The schematic of the column test is shown right here. We had 2 columns suspended vertically. One had a BSM depth of 12 inches and the other had a BSM depth of 18 inches. Both has a choke stone of 3 inches on the bottom. The columns were flushed through 4 times. Then we used deionized water as the influent. And we ran it through, collected the samples, and sent it to the lab. Here are the results from the lab. The deionized water had an influent hardness concentration of less than 1 milligram CaCO3 per liter, and then the effluent samples had a higher concentration. This indicates that there's something within the soil that is leaching hardness. We also did a soil test. The soil test parameters are shown on this table. 3 soil tests were sent into the lab. One was an uninstalled media. The media that we use for both the column test and the soil test is the exact same media installed, but it just wasn't installed during construction. And then you can see Leland, we used the hand auger to get soil samples from the center of the cells. For the soil testing results, there were a couple things we're looking at. We were looking at the cation exchange capacity. CEC we expected to decline over time. As you can see, it remained fairly the same. The cation exchange capacity is the measure of a soil's ability to retain cations, which helps the pollutant removal. Washington State Department of Transportation requires a minimum of 5 milliequivalent per 100 grams of dry soil in their media. Another thing that we were looking at was the sodium. There was an increase in sodium in the media over time. Studies have shown that sodium loading from deicers can affect pollutant removal, and it could actually release pollutants that have been held in the media. For the results, we calculated the percent reduction. For the percent reduction, the negative values indicate that there's a higher pollutant concentration in the installed cells rather than the uninstalled media. Calcium and copper were 2 parameters that we saw a positive percent reduction, which indicates that there was less pollutant concentration in the installed cells than there were at the beginning. For future groups, some suggestions that we came up with is further research on hardness and total phosphorus. Another 2 parameters that we didn't test on but we recommend testing on is total nitrogen and total petroleum hydrocarbons. To recap, the goals of the study is to develop a better understanding of the 2 BSM depths, a 12-inch and an 18-inch depth. The second goal of this study was to compare bioretention cell pollutant treatment under cold climate conditions, specifically when deicer is applied. We did not find a statistic difference between the 12-inch and 18-inch BSM depth. However, there was a statistic difference for the influent and effluent samples. The only pollutant that we tested that met tape and ecology requirements was TSS, and that is mainly because we believe it's mechanically filtered versus these pollutant removals. So the TP, dissolved zinc, and dissolved copper did not meet the tape and ecology requirements for the project. Yeah. Thanks for listening.